Okay, let's talk about something painful. You're debugging that really elusive bug, the one that maybe shows up like once a month.
Yeah.
Two users hit the same record at the same time, and bam, the data is just wrong. It feels
Well,
totally random.
the classic concurrency nightmare. It's exactly these kinds of tricky race conditions that databases try really hard to manage, usually with transaction isolation.
Right, isolation. The idea is to make things predictable, even when lots of stuff is happening at once.
Exactly. Because if you don't handle it carefully, two transactions messing with the same data simultaneously can just lead to, well, chaos.
And the gold standard, the one that makes developers sleep better at night, is serializable isolation, isn't it?
That's the one. It basically guarantees that the final result is the same as if all the transactions ran one by one in some serial order. Doesn't matter how interleaved they actually were.
Simple, predictable. Sounds like the dream.
It is for correctness.
So why aren't all databases just set to serializable by default then? Just turn it on and forget about it.
Yeah, well, the catch is usually performance. That level of strictness, that guarantee, it often means the database has to use more locking or other mechanisms that can really slow things down and reduce how many transactions can run concurrently.
Performance, always the trade-off.
Always. So the reality is many really popular databases, even the ones that advertise themselves as, ACID compliant.
That's atomicity, consistency, isolation, durability.
Right, ACID. Even those often use weaker isolation levels by default.
And weaker means faster, but potentially riskier.
Exactly. These weaker levels, they open the door just enough for some of these really subtle, kind of dangerous bugs to creep in. You could end up with financial data being slightly off, or records getting corrupted, or just really confusing states in your application.
Okay, so just trusting the ACID label isn't enough. That feels like a bit of an anti-pattern maybe, especially for senior interviews.
Absolutely a major anti-pattern. You need to understand the specific isolation level being used and what guarantees it actually provides, and importantly, what anomalies it allows.
Which is exactly what we're getting into today. We want to unpack these weaker isolation levels, figure out the specific problems they don't prevent, like dirty reads or lost updates, and see how databases actually implement them.
Yep. The goal is to arm you so you can talk about these trade-offs confidently, justify your design choices, handle those system design interview questions about consistency versus performance.
Okay, let's map it out. There's sort of a spectrum of these levels, right?
Yeah.
Defined by the SQL standard, usually.
Yeah, typically four main ones are discussed. From weakest to strongest: read uncommitted, read committed, repeatable read, and serializable.
And we're focusing on the weaker ones that you actually see used a lot in the wild.
Right. Starting with probably the most common default baseline, read committed. It gives you two core promises. First, no dirty reads.
No dirty reads. Is that like reading data that hasn't actually been saved properly yet? Like a draft?
Pretty much. Imagine transaction A changes some data, but it hasn't committed yet. It might still roll back, right? If transaction B comes along and reads that changed data before A commits or aborts, that's a dirty read.
So if A then rolls back, B just read data that technically never existed in the committed database state.
Exactly. You might see, say, an updated bank balance, but the corresponding transaction log entry hasn't been written yet. Or you see data that just vanishes later. Your application ends up working with this temporary, potentially phantom state.
That sounds bad, like really prone to bugs.
It can be very confusing. So read committed prevents this. A transaction running at read committed will only ever see data that has been successfully committed by other transactions.
How does it manage that? Does it have to lock the data I want to read if someone else is busy writing to it?
Usually not for reads, actually. That's one reason read committed is popular. Most databases that implement it avoid read locks by essentially keeping track of the old committed value.
Oh, so if transaction A is updating something, my transaction B just reads the previous version until A commits.
That's the common approach, yeah. It remembers the old value. So readers don't typically block writers, and writers don't block readers in this specific scenario. That's why it's the default in lots of places. PostgreSQL, SQL Server 2012, Oracle 11G, MySQL.
Okay, so I only see committed data. That's the no dirty reads part. What was the second guarantee?
No dirty writes.
Dirty writes.
Yeah.
So that's preventing my transaction from overwriting changes made by another transaction that also hasn't committed yet.
Exactly. Let's use that used car example. Alice and Bob are both trying to buy the same car, listing ID 1234. Alice's transaction starts, updates the listing to show her as the buyer, but she hasn't committed.
Okay, uncommitted, right.
Then Bob's transaction starts, and it tries to update the same listing row to show him as the buyer.
Without no dirty rights, Bob could just stomp on Alice's change before she even commits.
Yep. And then imagine they both try to update the related invoice record. Maybe Alice updates her invoice, then Bob updates his, or maybe locking happens differently there. You could easily end up with the listing showing Bob bought the car, but the invoice record belonging to Alice. Total inconsistency.
Ouch. Yeah, that's properly broken data.
Right. So read committed prevents this. Typically, it does use locks for rights. When Alice's transaction modifies that listing row, it gets a write lock on it.
Okay.
If Bob's transaction then tries to write to that same row before Alice commits, Bob's write operation will simply block. It has to wait until Alice either commits or aborts, releasing her lock.
Got it. So read committed. I don't read uncommitted stuff, and I don't overwrite uncommitted stuff. Seems pretty reasonable. But you said it's still weak. What's still allowed?
The big one it doesn't prevent is something called read skew, or sometimes non-repeatable read.
Read skew.
This happens when inside your single transaction you read some data, then another transaction commits a change, and then your transaction reads again and sees the new data. So you see inconsistent state within your own transaction's lifespan.
Okay, like the bank transfer example, right?
Mm.
Alice has two accounts, $500 each, total $1,000.
Uh-huh.
A separate transaction transfers $100 from account 2 to account 1. So account 2 becomes $400, account 1 becomes $600. It commits.
Right. Now Alice starts a transaction running at read committed to check her total balance. First, she reads account 1. Let's say she reads it before the transfer commits. She sees $500.
Okay.
Then the transfer transaction finishes and commits its changes. Now, Alice's transaction reads account 2. It sees the new committed value, $400.
Ooh, so within her one transaction, she saw account 1 is $500 and account 2 is $400. Her total suddenly looks like $900. It looks like $100 just disappeared.
Exactly. That's read skew. Both the $500 she read first and the $400 she read second were committed values at the moment she read them. That's why read committed allows it. But the two reads together don't represent a single consistent point in time for her accounts.
Wow. Okay, that's not just annoying for a user checking their balance. I can see how that would be a huge problem for things like database backups or long analytics queries.
Absolutely catastrophic for those. Or for any kind of integrity check that needs to see the whole database or a large part of it as it was at one single moment. You need a consistent view.
So how do we fix that?
That brings us to the next level up, typically. Snapshot isolation.
Snapshot isolation. Sounds promising.
The core idea is really elegant. Each transaction gets to read from a consistent snapshot of the database, basically, how the database looked at the exact moment that transaction began.
Ah, like taking a photo.
Kinda, yeah. Any changes made by other transactions that commit after your transaction started are simply invisible to you until your own transaction commits.
So back to Alice and her bank accounts. If she was using snapshot isolation.
Her transaction starts, it gets its snapshot. Let's say at that moment, both accounts are $500. Even if that other transfer transaction, $100 from 2 to 1, runs and commits while her transaction is still reading, her transaction only sees the state from its initial snapshot.
So she'd read account 1 is $500 and account 2 is $500. Total $1,000. Consistent.
Exactly. It completely eliminates that read skew problem.
Okay, that sounds much safer for reads. How do databases actually do that? Keep these old versions around?
The most common technique is called multi-version concurrency control, or MVCC.
MVCC.
Right. Instead of updates happening in place, overwriting the old data directly, an update creates a new version of the data item, like a row.
So you might have multiple versions of the same row existing at the same time.
Exactly. When a transaction updates a row, it effectively does two things. It marks the current version as obsolete or deleted, often tagging it with the TXID, the transaction ID that deleted it, and it inserts a new version containing the changes, tagging it with the TXID that created it.
Okay, TXID, transaction ID. So everything's tagged. But how does my transaction know which version is the right one for its snapshot?
That's handled by visibility rules based on those TXIDs. When your transaction starts, say it gets TXID 12, the database knows which other transactions were already committed before TXID 12 began.
Okay.
Your transaction, TXID 12, can see a version of a row if 1, the transaction that created it committed before TXID 12 started, and D2, if it was deleted, the transaction that deleted it committed after TXID 12 started, or hasn't committed yet, or it was deleted by TXID 12 itself.
Whoa, okay, let me process that. It sees stuff committed before it started.
Yeah.
As long as it wasn't deleted by something that also committed before it started.
Exactly. And critically, it completely ignores any versions created by transactions that started after it did, like TXID13, the transfer, even if TXID13 manages to commit first.
Ah, that's the key for Alice's bank example. Her transaction 12 starts. The transfer 13 starts later, updates accounts, creating versions tag 13, and commits. But Alice's transaction 12 never sees versions created by 13 because 13 started after 12.
Precisely. Her view is frozen at the start. It's really powerful. And a huge benefit is that readers don't block writers, and writers generally don't block readers because writers are creating new versions, not messing with the old versions the readers might be looking at.
So performance is generally pretty good.
Yeah, usually much better than serializable while offering much stronger consistency than read committed. Those old, unneeded versions get cleaned up later by a garbage collection process in the database.
Makes sense. And that's why snapshot isolation, or something very like it, is used in PostgreSQL, MySQL with the InnoDB engine, Oracle SQL Server.
Right. They all offer it, though sometimes under different names, which we should probably talk about later. The MVCC implementation details can vary too, like how indexes handle multiple versions, maybe append-only B trees like in CouchDB or Datomic.
Okay, so we've tackled dirty reads, dirty writes stopped by read committed, and read skew stopped by snapshot isolation. But I know there's another big one that interviewers love to ask about, the lost update problem.
Oh yeah, lost updates. Definitely a classic concurrency issue and prime interview fodder. It's a specific kind of conflict between two transactions that both try to write.
And it happens during what you called a read, modify, write cycle.
Exactly, that pattern. Transaction A reads a value. Transaction A modifies that value in its own logic. Transaction A writes the new value back.
Okay.
The problem occurs if transaction B does the exact same thing concurrently based on the same initial read.
Like incrementing a counter. The counter is 5. Transaction A reads 5. Transaction B also reads 5.
Yep.
A calculates 5 plus 1 is 6, writes 6. Then B calculates its 5 plus 1 is 6, and it also writes 6.
And boom, the final value is 6. But 2 increments happen. One of them just got completely wiped out, overwritten, lost.
And this isn't just for counters, is it? I can imagine this happening if 2 people try to edit the same wiki page at the same time, maybe. Or adding an item to a list inside a JSON document.
Absolutely. Anytime your application logic involves fetching some data, making changes to it in memory, and then writing the modified version back, you're potentially vulnerable if someone else can do the same thing concurrently. So the interview question then becomes, how do you prevent this?
Right. What are the main strategies?
Well, the best and usually simplest way, if the database supports it for your specific operation, is to use an atomic write operation.
Atomic, meaning the database provides a single command that does the whole read, modify, write thing safely.
Exactly. Instead of you doing the read, calculate, write sequence in your app code, you tell the database, increment this counter using a single command like update counters, set value plus 1, where's key foo.
So the database guarantees that that specific command happens atomically without interference.
Correct. It handles the necessary locking or internal mechanisms to make that specific operation safe. You don't have to manage locks yourself.
Okay, so rule 1. If the database has a built-in atomic way to do what you need, like increment or append to a list, use that. Don't DIY the read modify. Write it in your app code.
Definitely the preferred approach. Databases like MongoDB have atomic modifiers for parts of documents. Redis has atomic operations on its data structures. A common anti-pattern, especially with ORMs, object relational mappers,
Right.
is not realizing that a simple object.value plus 1, object.save, might actually translate into that vulnerable read, modify, write cycle behind the scenes. You might need to use specific ORM features or drop to a raw query to use the database's atomic update.
Good tip. Okay, but what if my logic is more complicated? Like maybe in a game, before I increment the player's score, I need to check 3 other conditions based on the game state. It's not just a simple increment.
Right. If a single atomic database command isn't enough because your application logic is more involved, then you probably need to use explicit locking.
Explicit locking, meaning I tell the database to lock the data I'm about to read and modify.
Yep. You acquire a lock on the specific rows before you read them for your calculation. The common way in SQL is using the select for update clause.
Select it for update.
Okay.
So for that game example, you might do begin transaction, select score, condition 1, condition 2 from player stats where player read equals 123 for update.
That tells the database, lock this row for player 123.
Exactly. It usually acquires an exclusive write lock. If another transaction tries to get a for update lock on the same row, or just tries to write to it, it will block until your transaction commits or aborts.
So the sequence is begin transaction, select for update to lock the rows, then do my complex application logic using the data I just read, then update the rows, then commit.
That's the pattern. Knowing select for update and when to use it is definitely a positive signal in an interview. The danger here, I guess, is just forgetting. Forgetting to lock one of the pieces of data you read, or making a mistake in the application logic itself.
Precisely. Manual locking puts the responsibility entirely on the developer. It's powerful, but you need to be really disciplined and careful to apply it correctly everywhere it's needed. Missing just one spot can reintroduce the lost update bug.
Okay, so we have atomic ops, explicit locking. Is there anything more? Automatic?
Yes, sometimes. Some database implementations that provide snapshot isolation also automatically detect these lost update scenarios.
Oh, really? How does that work?
They essentially track which rows your transaction has read from its snapshot and which rows it intends to write. When you go to commit, if the database detects that another transaction has already committed a write to one of those rows since your snapshot was taken, it realizes there's a conflict, a potential lost update.
And what does it do?
It aborts one of the transactions, usually the one trying to commit second. The application then gets an error indicating the transaction failed due to a serialization conflict or update conflict, and it needs to retry the whole transaction.
Ah, okay. So the database prevents the lost update by forcing a retry. Which databases do this automatically?
This automatic detection is a feature of PostgreSQL's repeatable read level, Oracle's serializable level, which is actually snapshot isolation, and SQL Server's snapshot isolation level.
Wait, hang on. You said PostgreSQL's repeatable read. I thought repeatable read was another standard level. Doesn't MySQL and DB also have repeatable read?
It does, and you've hit on a massive point of confusion in the database world and a really common interview trap.
Okay.
The term repeatable read, as defined in the SQL standard, is somewhat ambiguous, and different database vendors have interpreted it differently or just used the name for their specific implementation.
So repeatable read doesn't mean the same thing everywhere.
Not at all. It's crucial. PostgreSQL's level, named repeatable read, is actually snapshot isolation, and it does include that automatic lost update detection we just talked about.
Okay.
But MySQL InterDB's level, named repeatable read, while providing snapshot consistency to prevent read skew, does not automatically detect lost updates. It's still vulnerable to them unless you use explicit locking for update or other techniques. Some other databases, like IBM DB2, might use the term repeatable read to mean full serializability.
Wow. Okay, that's really important. So if someone says we're using repeatable read, you basically have to ask, okay, which database and what specific anomalies does that database's repeatable read prevent? Does it stop lost updates?
Exactly. That clarification shows much deeper understanding than just accepting the label. Always ask about the phenomena prevented, not just the name of the level. Big interview tip there.
Definitely noted. Okay, so atomic hops, explicit locking, automatic detection, and some snapshot implementations. What about compare and set? I hear that mentioned sometimes.
Compare and set, or CAS. Yeah, that's another technique, often used when you don't have full transaction guarantees, or maybe in slightly different contexts. The idea is optimistic.
Yeah.
You try to perform the update, but you include a condition that checks if the data has changed since you read it.
So back to the wiki page example. I read the content. Let's say it was old content. I edit it to new content. My update would look something like, you update wiki pages, set content, new content, where it equals 1234, and content on its old content.
Exactly. The where clause checks if the content is still old content. If someone else snuck in and changed it to intermediate content and committed, your where clause will fail. No rows match, and the update won't affect any rows.
And the fact that 0 rows were updated tells my application that there was a conflict and I need to retry. Like, reread the intermediate content, reapply my changes, and try the CAS update again.
Precisely. It's a way to detect the conflict at right time.
Seems pretty clever. Is it always safe, though? Does it reliably prevent lost updates?
Not always. It depends subtly on how the database evaluates that where clause in relation to its isolation level.
How so?
If the database might evaluate the where content in the old content part based on an older snapshot, which can happen in some weaker isolation modes or specific MVCC implementations, it might think the content is still old content even if another transaction has actually changed it and committed.
Oh, so the condition could pass incorrectly, and my update goes through, overriding the other person's change. A lost update happens despite using compare and set.
It's possible in some scenarios, so relying only on compare and set in your application logic without verifying that the database's specific isolation guarantees make it safe for preventing lost updates. That's another potential anti-pattern. You have to be careful.
Okay, that's a really subtle trap. Got it.
Yeah.
Now, how does all this thinking change when we move beyond a single database node, like into distributed systems with replication? Locks and compare and set seem tricky if writes can happen on different replicas at the same time.
Yeah, you've hit the nail on the head. In replicated systems, especially multi-leader or leaderless ones where writes can happen concurrently on different nodes, traditional locking or CAS based on a single authoritative version often breaks down or becomes incredibly complex and slow.
So what happens then? Do you just accept conflicts?
Often, yes, you have to design for the possibility of concurrent writes creating conflicting versions of the same data item. Sometimes these are called siblings.
Siblings, okay.
And then you need a strategy for resolving those conflicts later. This might happen automatically based on rules, or it might require application-level logic to merge the conflicting versions intelligently.
Merging. That sounds potentially complicated.
It can be. Some types of operations are easier, though. If your operations are commutative, meaning the order they happen in doesn't affect the final result, then conflicts are less of an issue.
Commutative, like incrementing a counter.
Yeah.
Adding one, then adding one is the same as adding one, then adding one. Or adding unique items to a set.
Exactly. Operations like those are inherently conflict-free in many distributed scenarios. Some databases, like React 2.0 with its CRDTs, conflict-free replicated data types, were specifically designed around this principle.
What about that strategy called last write wins? I hear that a lot with distributed systems.
LWW, last write wins. Yes, it's very common because it's simple to implement. You just need timestamps, and you keep the version with the latest timestamp, discarding any others that happened concurrently.
Sounds easy. Too easy.
Often, yes. It's incredibly prone to lost updates. If two writes happen concurrently on different nodes, the one with the slightly later timestamp completely obliterates the other one, even if they were based on the same initial state. It's basically accepting data loss silently. Unless your data or operations are structured such that LWW is provably safe, which is rare, it's generally considered an anti-pattern for data integrity. In a system design interview, you'd want to show you understand the risks of LWW and can discuss more robust conflict resolution strategies.
Right. Okay, wow. We've gone from the basics of reading committed data all the way to merging conflicts in distributed systems. That's quite a journey.
It covers a lot of ground, yeah. These concepts build on each other.
Let's try simulating a couple of quick interview questions to tie some of this together. Ready?
Sure. Hit me.
Okay, first one. Can you explain the practical difference between read committed and snapshot isolation, specifically in terms of the anomalies they prevent?
Okay, well, both prevent dirty reads, so you won't see uncommitted data. Read committed also prevents dirty writes, so you don't overwrite uncommitted data. But read committed allows read skew, or non-repeatable reads, where you might see different states of the database within the same transaction. Snapshot isolation prevents everything read committed does, plus it prevents read skew by giving the transaction a consistent view from when it started. So the key difference is snapshot isolation eliminates read skew.
Good. Clear focus on the specific anomalies. Okay, next one, scenario-based. You're designing a system with a large database. It needs to handle frequent short customer transactions, like placing an order, but also support long-running analytical reports that need a consistent view of the data. What isolation level would you recommend and why?
Okay. Frequent short writes, long consistent reads. I'd lean towards snapshot isolation for this.
Why snapshot?
Well, a few reasons. First, performance is generally good because, as we discussed, readers don't block writers and vice versa under MVCC, which is crucial for handling those frequent customer transactions without them getting stuck behind the long reports. Second, it provides that consistent snapshot, which is exactly what the analytical reports need to avoid read skew and get accurate results. Read committed wouldn't give the reports that consistent view. And while serializable would also give consistency, it might impose too much of a performance penalty on the short transactions due to increased locking. So snapshot isolation seems like the best trade-off here between performance and consistency for both use cases.
Nice. Justifying the choice based on the specific requirements and trade-offs. Excellent.
Yeah, explaining the why is key.
Okay, let's try and wrap this up with the key takeaways then. We started with the basics.
Right. Read committed being the common default. It stops dirty reads and dirty writes. You only see committed data. You only overwrite committed data. But it still allows read skew.
Then we move to snapshot isolation, usually built with MVCC. The big win there is the consistent snapshot from the start of the transaction, which eliminates read skew. Great for reports, backups, anything needing that stable view.
And we spent a good chunk of time on the lost update problem, that read, modify, write cycle danger.
Yeah, solutions there included using the database's atomic operations whenever possible.
The best option if it fits.
Using explicit locking with select for update if the logic is complex.
Requires discipline, but powerful.
Relying on automatic lost update detection if your database offers it under snapshot isolation, like in PostgreSQL's repeatable read, Oracle's serializable, SQL Server Snapshot.
Less error-prone than manual locking.
And using compare and set carefully, understanding its potential pitfalls depending on the database guarantees.
Right, not always a silver bullet.
And maybe the biggest warning label was around the name repeatable read. It means different things in different databases.
Absolutely. Always clarify the specific guarantees. Don't just trust the name.
Ultimately, choosing an isolation level isn't just ticking a box. It's a critical design decision, right? It's balancing how much consistency you absolutely need against the performance you can afford.
Exactly. And understanding these nuances, these different failure modes or anomalies, is just fundamental to building reliable systems. And yeah, definitely key for those senior engineering interviews.
So a final thought for everyone listening. Take a look at the systems you use every day. What database is it? What's its default isolation level? Are you potentially vulnerable to read skew or maybe even lost updates without realizing it?
It's a really worthwhile exercise. You might be surprised what you find.
We really hope this deep dive helps you navigate these tricky concepts more confidently. If you found it useful, definitely hit that like button and subscribe for more content like this.
And please drop a comment below. We'd love to hear about your own battles with concurrency bugs or any interview questions you've faced related to transaction isolation.